Hey everyone, this is Dr. Walker. In this video, we're going to go over one more example, finding the electric field due to a continuous charge distribution. This time, it's going to be a charged disk. So we have a charged disk and we're trying to find the electric field at point P. You might find that this is similar to the problem that we just did, finding the electric field due to a charged ring. When we did that in the previous video, this is the result that we found for the electric field due to a charged ring, and it pointed in the x direction. So what we have to do now is figure out this problem, and it's going to be a little bit different because we can think about how we can use this charged ring to help us. We can think of the disk being made up of an infinite number of these rings. And then we can look at the contribution of one of these rings and then sum up the contributions of all of the rings. So if we realize that, we're going to set up the problem a little bit differently than we have been. In the previous problems, so don't write this down because I'll erase it in a second. In the previous problems, we've been writing dE equals KE dQ over R squared. We found the contribution from very tiny, small charge elements and integrated over the entire charge distribution. This time, we're going to find the contribution of one of these rings. So the dQ is not going to be a tiny little element. The dQ is going to be the whole ring. So that means instead of using KEQ over R squared, we're going to use our result from the previous video. The only change I've made is I've called the radius A here instead of R. I just didn't want to get the R's confused because our disk here has a radius R. But now our ring actually has a radius with a lowercase r. And we know that we're going to have to integrate from 0 to capital R to get the contribution of all of these rings of different radii. So we're going to write dE equals KE x, and then the charge on one of these rings, since dE is the field created by one of these rings, the charge is dQ. And then x squared plus, and then this is the radius, but it's lowercase r. That's the variable we're going to integrate over. So that's how we set it up. And then we have to figure out the variable that we're going to integrate over, which is going to be r. So we need to make sure that everything that depends on r is written in terms of r. So hopefully you can see that the dQ actually depends on r. Might not be super obvious, but you can write dQ using its definition, sigma dA. That's the definition of dQ. So what is dA? That's area of that ring, right? So the area is going to be 2 pi r dr. The circumference times the width. Dr is the width of that ring. So we're going to make that substitution. For dE, we'll get KE x sigma 2 pi r dr over x squared plus r squared to the 3/2. Another difference between this problem and the previous one with the ring is when we did the ring, that the distance from that ring to that point, it stayed constant, right? And so we chose to integrate over the angle. But in this case, we're integrating over r. The distance x, though, is still staying constant. All of these rings are distance x from the point P. So really, one of the hardest things is just figuring out the variable that we're going to integrate over. Now we can write our expression for the electric field. We're going to factor out the variables that don't depend on r. So KE, x, sigma, and pi. And then I'm actually going to leave the 2 inside the integral because it's going to help us perform that integral. So 2r dr over x squared plus r squared to the 3/2. We're going to integrate that from 0 to capital R, so we get a contribution of all of these rings that make up this disk. You should be able to perform this integral if you use substitution. This will be your u, and that will give you the integral of u to the negative 3/2. So you should be able to perform that integral, and the result is going to be E equals ke x sigma pi, and then we're going to have x squared plus r squared to the negative 1/2 divided by negative 1/2. That's going to be from 0 to r. So let's go ahead and plug those values in. Kex sigma pi, and so we have x squared plus capital R squared to the negative 1/2. And actually, let me bring that negative 1/2, let me bring that to the top here and call it negative 2. And then we're going to subtract. Again, let me bring that negative 1/2 over. It's going to be negative 2. And then the r squared is going to be 0, so it's just going to be x squared to the negative 1/2, which is x squared, which is x to the negative 1. So we can let's just simplify this a little bit more. We're going to get kex sigma pi, and let's go ahead and factor out a 2 already. And then we're going to get negative 1 over x squared plus r squared, the square root of that. And then we're going to get plus 1 over x. And finally, we can go ahead and distribute the x over here. So we're going to remove it from here, and we're going to put it over here, multiply both sides by x. So it will just give us 1 over here. So the final answer, hopefully you can see what it is, for the electric field at point P is going to be Ke times 2, let's say 2 pi Ke sigma times 1 minus x over square root of x squared plus r squared. And all of that is going to be in the x direction. The reason I wrote the 2 pi Ke first here is because we can also rewrite this in terms of the permittivity of free space, and we'll actually do that in the second part of this example. So we found the electric field due to this charged disk. In part B here, we want to say, well, what happens if this disk is actually an infinite plane of charge? So that means that this disk is really, really big. R is approaching infinity. If you're thinking, well, what's the point? When do you ever have an infinite plane of charge? You can think about this being equivalent to x being much, much smaller than r, right? If you're really close to the disk, then it's as though to that point, it's as though that disk is infinite. So I've written down our result from the previous slide, and we want to see what happens as r approaches infinity. What happens to that field? Well, if we look at r here, if it approaches infinity, then we're going to get infinity in the denominator, and this whole term is going to cancel out to 0. So we're going to get 2 pi K sigma. And then using the relationship between Coulomb's constant and the permittivity of free space, we have permittivity of free space is 1 over 4 pi Ke. So we can also rewrite this as sigma over 2 epsilon 0. And so that is the electric field due to an infinite plane of charge, and we're actually going to see this again, so this is going to be a very useful result. Hope this was helpful. See you next time.